So, oh, okay. Hey guys. So I'm back and trying to maneuver over to the right page. Ugh, I really hate this whole Zoom bar being at the top thing. It's very frustrating, but I'm gonna do my best here. Okay, so we're gonna get started with the chapter 2.3. So this chapter has to do with matrix multiplication. It has to do with compositions. And I think it's really interesting. So we're going to start out coming back to an example that we sort of used before. And it's really just an idea, which is a while ago we talked about sort of coding and encoding as a way to bring us into talking about inverses and transformation matrices. We're going to use this idea again, but instead with compositions. So we're going to draw a little triangle. Over here, we've got X. Right here, we've got Y equals sine of X. Which brings us to our Y. From there, we use the equation Z equals cosine of Y. To bring us to Z. Which means that this line right here is equal to, in other words, Z is equal to cosine of sine of X. So this should not be too difficult for us. It's the idea of compositions of functions, something that we've all probably studied before to some extent, at least a little bit. But the idea is that we can bring this over to functions. Because the basic idea is, say we've got a vector, X. It consists of X1 and X2. We've also got a vector Y consisting of Y1 and Y2. Okay, so from there, what we're going to do with them, we're going to basically say that we've got the same sort of situation, but this time it is with matrices and vectors. So we'll draw out our triangle again, our kind of sideways triangle. I'll get a different pen color. So we've got the vector X, the vector Y, and the vector Z. And in between, we've got vector Y equals matrix A times vector X. And we've got vector Z equals matrix B times vector Y. Which means that this line right here becomes, you guessed it, it then becomes Z, or vector Z equals B times A times X. Okay. So, and that would be a composite of the vector Y equals A times the vector X and the vector Z equals B times the vector Y. So this is the basic idea of compositions of matrices, which will lead us into talking about multiplying matrices times each other. So I'm going to erase, and we're going to move on to talking about whether this is linear or not, whether compositions of matrices are still linear. Now, I'll remind you, the way we determine if something is linear is by using the definition that we got of linear a little while back. And that definition is a theorem that basically says, and I won't go through the whole thing, but okay, that's good enough. But it's a theorem that puts things in terms of T of vector V plus vector W equals T of vector V plus T of vector W. And as a theorem that also says that to be linear, this has to be true as well. T of K times vector W has to be equal to K times T of vector V. So basically we need to prove that for when we've got a composition of matrices. So how do we do that? Basically what we say is we set this equal to B of A times vector V plus, big surprise, vector W. And what we learn is that we can turn this into B of vector A, or of A times V plus A times W, because we just distribute out, right? And we can further go from there if we distribute again to say that B times A times vector V plus B times A times vector V. All right, so we've got that right there. This is of the same form as this. So we can turn a matrix composition situation into what we need to prove that it's linear. Let's do the same thing for this K part. So we start with B of A of a scalar K times a vector V, right? And then, well, let's look at what we can do. Based on the matrix algebra, and I should remind us that all of this right here is based on the basic algebraic rules that we learned very much in the beginning of, the ability of scalars to be commutative and the ability of us to be able to distribute is really the two laws that are coming into play here. And we just kind of use them in this scenario. So you can take this, and based on what we know about scalars being able to move around, we can change it to B of K times A times vector V. And then from there, we can go a step further because we can move K out one more time and change it to K of B times A times vector V. Right? Now, this should look very familiar because, again, it's the same form right here as this K times T of vector V. So this proves right here that compositions of matrices are linear, right? Now let's figure out, before we write our big, our basic proof about the idea of these compositions of matrices, or what we're going to call products of matrices, let's kind of establish how we would actually compute this. How would we actually find the answer of two matrices multiplied times each other? So to do that, we're going to do a little bit of theoretical proving, just kind of like we did here. We're not going to use any real numbers, but we will definitely be using real numbers later on to kind of show how all of this stuff works in action. But let me just finish erasing. Okay. So to compute the matrix, what we really want to figure out is, so to find the matrix, because here's the second part. What we really need to figure out is, to be able to know how to multiply these two things, we need to know what the matrix is going to be, like what the final matrix is going to be, the form that it's going to be in. So the way that we do that. So in normal scenarios, we would have T of vector E1, right? Like this would be how we would sort of operate if we didn't have matrices being multiplied times each other. So that means that we have to turn this into our new scenario. So in other words, B times A times vector E1, right? And so that means that T of E2, and I've got to remind us that these E's are the standard vectors. And so these E's, this E1 is going to be 1 0 0, this E2 is 0 1 0. And so that becomes B of A times E2, right? And from there, let's look at what we can really figure out. So what does B times A times this E really mean? What it really means is B times the first column of A. So let's turn this into real numbers, okay? Because what we need to understand is that in a normal matrix, it's composed like this, right? A equals T of E1, T of E2, all the way down the line. This is kind of how we define our column vectors and really the matrix as a whole. So let's kind of turn this into some numbers. We know that, let's say we've got a matrix 6, 7, 8, and 9. And we want to multiply it times the matrix, or we want to multiply it times the matrix 1, 3, 2, 5. So if we're going to do B, so let's say if we're looking first for the version of this, that's going to be B times the first column, right? So that's, in other words, going to be these two things times this. And if you compute that, what you should end up with is 2735. Then we have to deal with this second column, our new version of the TE2. So how do we do that? We have these two things again, but this time times this. And what we get here is 4761. So what's our final matrix? Well, if you just get rid of these two lines right here, that's it. This is our final matrix. So it's really quite simple. You just have to break it down into its component parts. So that leads us into our main theorem that starts off this whole show, basically. So I'm going to erase this. Hopefully that all made sense. Shouldn't be too bad yet. Okay. From here, I switch back to the black marker. Okay, so we're going to start with our theorem. The product of matrices T of X is equal to B of A of vector X. It's a horribly drawn X. The product of these two things is B A, or the product of these two matrices, which means, in other words, that B times A of X is going to be equal to B A times X. Right? Because if this is our total, if this is our big matrix, right? Or a big matrix, that's going to have to be the same thing as multiplying A times X and then that times B, right? But now let's think about something a little bit more complicated. Let's sort of complicate this definition a little bit. Because say we come back to this triangle example. Say we've got this going on again. But say instead, well, first let's point out that when we're moving from X into Z, let's think about the spaces that are happening here. Because let's say that B is an N times P matrix. And A is a P times M matrix. That means that we're moving from M to N, right? Because the P's cancel out and we start out with A. So if we were to draw that out here, actually, sorry, this should have been drawn, I flipped it around. It should have been drawn like that. Okay. So we've got our vector X, but we know that it's in the subspace of M. And then we move to Y, we know that's in the subspace of P. So that means that finally our last subspace, our final subspace, is N. Right? We move from M to P to N. But what if we were to suddenly say that we've got the same drawing again? So we start out in RM with our X, and we end up in Rn with our Z. But in between, to go from X to Y, that takes us to a space of Q. But to go from Y to N, the other Y is at a space of P to N. Would these two things work? Would we be able to actually use this? Would we be able to use this as a composition if there are two Y's? In other words, Y's in two different spaces. What we really need to understand is that we can't do this. This isn't possible, right? And that makes sense just on a logic level. But we need to know that to lead us into our next theorem that sort of nuances things a little bit. So let's see. Okay, so our next theorem is that if we've got B equaling an N times P matrix, and we've got A as a Q times M matrix, these two equal each other if and only if P is equal to Q. Now, if we've got B is equal to an N times P matrix, and A is equal to a P times N matrix, a P times M matrix, then the product of B times A is going to be the matrix of linear transformation, which means that, say we change this now, these both become P matrices, P spaces. We know that they're equal, P and P. So if that's true, then B times A is the matrix of linear transformation where T of X equals B times AX. And this is just rehash really from the old theorem. It's really just combining them together. And as we already pointed out, I'm not going to point it out again, but we could, change these groupings around, change the association. Okay, so the next thing that I would like to talk about is the columns of a matrix product. And then after that, I think I'm going to end this video and come back with a part 2. Okay, so the columns of matrix product. So if we are going to continue with this line of thinking that B is an N times P matrix and A is a P times M matrix, we want to figure out how to write the matrix product in terms of the columns. So let's say that we started with this idea. We've got B times A times E1. We've already kind of looked at this when we looked at columns previously a little bit. But what I really want us to understand is that this becomes B times V1, V2, all the way on, etc., of the A matrix. And when you multiply that out, it becomes BV1, BV2, all the way down the line. So if you break it up where you've got one matrix just kind of as its whole part, and then you're multiplying that times the columns of the other matrix, it can kind of help you see how what we just did with the actual real numbers, how that actually works. And that brings us to our next theorem, which I don't need to write out because it's really just the formal version of exactly that. Now let's talk about commutativity. Let's talk about whether or not this system is commutative, whether or not matrix multiplication is commutative. The thing that's important to figure out is that we started this lesson by talking about compositions of functions, right? And something that we should know is that compositions of functions are not commutative. And if you need a refresher, commutative means that you can switch the numbers around and you'll still get the same answer. And in general, we know that that's not true when it comes to compositions of functions. So as you would expect, it's also not true when it comes to compositions of matrices. However, we've got our next theorem. A times B does not equal B times A. However, every once in a while it will. And when that is true, we say that those two matrices commute. We're going to want to remember this word. It's going to come up and it's going to be important. So if that is true, if AB does equal BA, then we're going to say that the matrices commute. Okay. Now let's talk more about properties. Really, this lesson is just really about properties of matrix products and figuring out how to multiply them. So we're going to talk about the entries of a matrix product. So we're going to figure out the ijth entry of BA, where BA is an n times P matrix, or where A is an n times P matrix and B is a P times M matrix. So the ijth entry of product BA is really going to be the ith component of vector B times the of matrix B times V times the vector VJ, right? So what I mean by this is the way that I'm going to write this, I'm going to just jump right into the theorem. If we've got BA equals, we've got this matrix right here where we've got B11, B12, all the way down to B1P. We've got all the way down to B11, B12. Sorry, this should say an I. BI1, BI2, all the way out to BIP. And we continue on down, and then we're multiplying it times A, where we've got A11, A12, A1J, and we continue it on down to A1M. And if we continue that all the way down to AP1, AP2, to APJ, all the way out to APM. So, we're trying to find the ijth entry, right? So that would mean, in other words, that we're trying to find, it'd be very nice if I could highlight. No, it's fine. But that means that we're trying to multiply this row times this row, right? Because here is I and here is J. The way we're going to do that is the dot product method. Because we say BJ, sorry, B, oops. Try that again. B1J times A nope, sorry, messed it up again. Honestly, I and J are very close to each other as letters, which is very frustrating. But you've got BI1 times A1J plus bi2 times a2j all the way out to b I p times a p j. That is how you would find those specific entries. Another way we can write this is using sums. First of all, I want to point out that I'm about to use the scary sigma sum, this thing. It always looks really overwhelming to me as well. But really it just means like summing with addition, summing from one number to another number, like with addition, all the numbers in between, adding them all up. So the way that we can summarize this is when we've got a sum from k equals 1 to k equals p of b I k times a k j. It's just a condensed way of writing this. But this is really what you need to worry about, because this is just how we would write this, like finding this specific entry or this specific these specific entries. So that's another important property to keep in mind. Really, this chapter is outlining, how to think about this. And it should be pretty familiar because in a lot of ways it resembles how we learned to think about basic matrix multiplication, or basic matrix multiplication and vector multiplication before we added in the matrix products. And really the matrix products is just an extension of what we've learned on matrix multiplication and vectors and scalars and all of those algebraic properties. So it shouldn't be too bad. A lot of it follows the same logic. But the next thing I would like to go over with us is going back to the idea of transitions, of transition matrices, and of different types of, reflections, orthogonal projections, etc. Because I want to explain kind of a cool thing that the book shows us. So it says that we're going to set A equal to 0, 1, 1, 0. B here is 1, 0, or negative 1, 0, 0, 1. BA is equal to 0, negative 1, 1, 0. And AB is equal to 0, 1, negative 1, 0. Now, these are all transformation matrices. I'm not going to write this down, but A is a reflection about the vector 1, 1. B is a reflection about the vector 0, 1. BA is a rotation through pi over 2. And AB is a rotation through negative pi over 2. And I'm going to prove this by just using one example. So we're going to return to the trusty L-shaped graph thingy that we like to use a lot. Starting with this. This is vector 0, 2, which we can see because it's over 0 up 2. And this is vector 1, 0, which we can see because it's over 1 up 0. We're going to draw in that line of 1, 1 that I said that the first matrix reflects everything over. Oh, I thought we were going to draw it in. Okay. So we're going to draw the vector 1, 1. And we're going to put to use the first matrix. A. So if we do that, then that means, well, let's see, what does that mean? We take the matrix 0, 1, 2, 0, or 0, 2, 1, 0, and we multiply it times 0, 1, 1, 0. So what does this mean? Well, if we're going to go about solving this, we're going to first do this, right? So we've got 0 times 0 plus 2 times 0, which is 0. Then we've got 1 times 0 plus 0 times 1, which is 0 again. Now we're going to do all this times this column. So 0 times 1 plus 2 times 1 is 2. And 1 times 0 plus 0 times 0 is 0. Right. So what does that mean? Actually, wait a minute. I think this is not right. Let's see. We've got 0 times 0 plus 2 times 1. Ah, I see. This should be a 2. And we got 1 times 0 plus that's a 1. 2. And that should be a 1. But this should be a 0 limit. Sorry. Sorry, guys. Mental math mistake. So we've got 0 plus 2. So that's 2. 0 times 1 plus, yes. Okay. So this should be a 0. So the final matrix should be 2, 0, 0, 1. Right. Okay. So if we move on to drawing that onto our L, what does that give us? Well, it gives us a reflection over 1, 1. Because if we look, this right here flipped to be over here, and this right here flipped over to be right here, right? So then if we want to multiply further by B, that means that we're going to have 2, 0, 0, 1 times, and then what did we say B equals? Times negative 1, 0, 0, 1. Okay, so we're going to do the same process. So first we're going to have 2 times negative 1 is negative 2 plus 0 times 0. So we have negative 2. Then we have 0 times negative 1 plus 1 times 0, 0. Next we move over this column. So we've got 2 times 0 plus 0 times 1, 0. We've got 0 times 0 plus 1 times 1, 1. Now, what is this going to leave us with? Well, if we plot this onto our L shape, we end up with this. We actually have to move over into the negative quadrant and go over negative 2 up 0 and over 0 up 1. Now, from A to B, we see that that was a reflection about 0, 1. But if we look or from B to the final, or from A to B. But if we look from the beginning to the end, in other words, we take this very beginning image and we look what happens when we multiply it times AB as a whole. We went from here to here, and lo and behold, if that is not exactly what AB is, In other words, a rotation through negative pi over 2. We started here and we flipped over negative pi over 2, or negative 90 degrees. So I just thought that was a cool way of tying it back into transformations. But I'm going to end the video here, and I'm going to come back for a part 2 of this lesson. There shouldn't be too much more left of it. And then I'm going to try to get to some of the questions that Dr. Prudhomme and I covered in this week's lesson. But I hope that you all enjoyed so far this lesson. I actually think it's one of the more simple ones for sure. Much more straightforward, I think, than last week's. Last week's, I think, was probably one of the longest and probably one of the most tedious for everyone to probably get through and watch. But hopefully this one is a little bit better. So